Okay, in this video I'll be talking about measures of variation, also known as measures of dispersion. So let's look at this introduction. It says at Big Bank, customers wait in 3 lines for 3 different tellers. At Best Bank, customers wait in 1 line for 3 tellers. The following values are wait times for 11 customers at each bank. So on number 1, it says determine the mean for each set of data. And then number 2, it asks you which bank has the more fair system. So I would encourage you to do this problem and then watch the video. So for Big Bank, you should have gotten a mean of 7.2. For Best Bank, you get the same mean. But if you look at the data, is it really the same? Well, our mean is the same, but it doesn't mean the data is. In fact, there's more to the story here. So which bank has a more fair system? Well, most people would probably say Best Bank because the wait times are more equal. It's a more fair system. If you're at Big Bank and you waited 4.1 minutes, then you're probably pretty happy because you got in there pretty quick. But what if you're on the other end and you waited 11 minutes? You might be asking to talk to the supervisor. So if you look at the times for Best Bank, they're a lot closer together. In fact, I want to make a comment here. The data is more spread out for Big Bank. In fact, you can also see that in the graphs. At Big Bank, things are more spread out. At Best Bank, they're more the same. All right, let's go on to the next slide. So here it says, for definition, measures of dispersion are used to measure the spread of data. And so really, when we're finding measures of dispersion, we're answering this question here. How spread out or how spread apart is the data from the mean? So I'm going to give you 3 graphs. And you can see on the first one here, the data is not all that spread out. Most of it's very close to the mean. And so we would say this has a low measure of variation, or the measure of variation would be low. In the middle graph here, you can see things are a little bit more spread out. This would be a moderate measure for variation. And then finally on the last one, you can see that the data is quite spread out, and so we have a high measure of variation. And so the first one we're going to talk about when we talk about measures of variation is the range. And this is one that I would guess most of you are familiar with. The range for a set of data is found by finding the difference in the highest and lowest data values. So it says find the range for the wait times at Big Bank and Best Bank. So again, you can go ahead and do this problem and maybe number 4 and then check your answers. So for Big Bank, if you subtract the lowest and highest wait times, 11 minus 4.1, you get 6.9 minutes. So about 7 minutes. At Best Bank, when you subtract the lowest or the highest minus the lowest wait times, you get 1.2 minutes. And so you can see from the range, this is giving us more information now. You can see at Best Bank, there's less variation in the wait times. So let's look at number 4 now. So you're supposed to find the mean in the range. So for Mrs. M, the mean is 8.25, and the range is 7. For Mr. T, the mean is 6, and the range is also 7. So even though the ranges are the same, if you look at the data, they're really quite different. In fact, for Mrs. M, notice most of the students got an 8 or a 9. This is an outlier here, this 3. Whereas with Mr. T, you can see that the numbers are more spread out. And so it's really misleading if you just look at the mean and range here because of that 3, the outlier for Mrs. M. So we have another measure of variation that is a more precise measure in terms of how spread out the data is. In particular, it's very useful in comparing or to see how far any piece of data is from the mean. So let's go ahead and talk about this one. It's called standard deviation. The standard deviation of a set of data is used to measure how much the data differs from the mean. So it says, consider the charts below which indicate the average high temperatures for Phoenix, Arizona, and Honolulu. So first of all, we're supposed to find the mean temperature for each city. Again, I would encourage you to do number 1 and 2 and then watch the video. So for Honolulu, the mean temperature, you should get 84.75 degrees. For Phoenix, you should get 84.3 degrees. So if this is the only measure you had and you didn't know anything about these two locations, you might think that the climate there is very similar. The average temperature or the average highs throughout the year are pretty much the same or very close. But in reality, and you can see this by just looking at the charts here, you can see that in Phoenix, Arizona, the high temperatures are much more spread out. Whereas in Honolulu, seems like it's always in the 80s. So, or at least average highs are. So there's more to the story here. So if you find the range, that starts answering the question here. So for Honolulu, if you subtract your smallest from your highest average, you get 9 degrees. And if you do the same thing for Phoenix, you get 104 minus 65, which is 39 degrees. And so you can see the range is much bigger for Phoenix. And so now we're starting to get a better picture of what's really going on here. And in fact, standard deviation will give us an even better picture. All right, so let's move on to the next slide. But before we do that, let me just make one more comment here. The greater the spread of data is from the mean, the larger the standard deviation. So if you have a small variation from the mean, then you're going to have a lower standard deviation. Okay, so what we were just talking about, you can see on the charts, there's very little variation here, whereas with Phoenix, you see it more. Now, below it says standard deviation for each. So what I want to do here is I want to give you a good understanding of what standard deviation means. Or I want to make sure you can explain it. So for Phoenix, 14.9% is the standard deviation, and which means it's basically about 15%. Now it turns out evaluating standard deviation is time consuming, especially if there's lots of data here. I'm just giving you the answer here. And then we'll talk more about how to find standard deviation. So what does this mean that the standard deviation is 15 degrees? Well, on average, the average high temperatures, or the average high temperature, is about 15 degrees from the mean. On average, the high average temperature is about 15 degrees from the mean. So you can see it's not very close to the mean on average. With Honolulu, the standard deviation is about 3.19, so about 3%. So on average, the average high temperature in Honolulu is about 3 degrees from the mean as you look throughout the year. So you can see that the temperatures are staying a lot closer to the mean. All right, so on number 5 it says find the deviations from the mean for the months of January, March, and July for each city. So I want to do this, and again, what the whole goal here is to try to make sure we understand what standard deviation really means. So first of all, for Phoenix, the average, or the mean, is about 84 degrees. So I rounded that. In January, the average high, and these are all average high temperatures. In January, the average high is 65. So I want to find the deviation from the mean for January. So I take the data value 65 and I subtract the mean, which is 84, which tells me I'm 19 degrees below the average, or I should say below the mean. In March, the average high temperature is 74 in Phoenix. So again, if we want to find the deviation from the mean, it's the data value minus the mean. So here we get negative 10, which tells me in March we're about 10 degrees below the mean for high temperatures. And then finally, I'm looking at July here, which has an average high temperature of 104. And so if you subtract to find the deviation from the mean, you get 20. So in July, on average, we're 20 degrees above the mean. And so just looking at these 3 months, it seems reasonable that on average we're about 15 degrees from the mean in Phoenix for high temperatures. All right, let's do the same thing for Honolulu. In fact, you may want to try this for yourself. So in January in Honolulu, its average high is 80. And so to find the deviation from the mean, it'll be 80 minus our mean, which is 85. So we get minus 5. So in January, the average high is about 5 below the mean. In March, the average high is about 82. And so if you find the deviation from the mean here, you get negative 3, which means on average in March, we're about 3 degrees below the mean. And then finally, let's look at July, where it's 88 on average for high temperature. And so subtracting to find the deviation from the mean, 88 minus 85 is 3. And so you can see in July, on average, we're 3 degrees above the mean. So if you look at these numbers here, you can see that on average, it's reasonable to think that we'd be about 3 degrees from the mean, which is what the standard deviation tells us. All right, let's go ahead and move on to the next slide. It says, Professor Martinez's students had a mean score of 75 with a standard deviation of 5. Well, basically, if you look at Professor Martinez, what that's saying is, on average, we're either about 5, within 5 of 75, so we could go as low as 70 and as high as 80 on average. Professor Stevens had a mean score of 75 with a standard deviation of 15. So on average, the scores are about 15 from 75. And so for Mr. Stevens, Professor Stevens, let's see, 15 from 75, that'd be 60, and 15 added to 75 would be 90. So the scores would range between 60 and 90 on average. So you can see, it says which professor had more students who did not pass the exam. That would be a 70. You could see that would be Professor Stevens. All right, let's look at percentiles next. I'm just going to mention this one because this is another measure of variation that I should at least mention to you here. It says a score in the nth percentile indicates that you outperformed n% of the population. So let's see what that means here. It says Steve had a score of 490 on the SAT math test. His score was reported to be in the 60th percentile. What does this mean? So what this is really saying is that Steve outperformed 60% of the students who took the SAT. So what that really, 50%, you'd be right in the middle, so really you could say he did better than average. Now, if you came home and you told your mom that you got 60% on a test, then you would have failed the test because 70% would normally be passing. Whereas here, 60% maybe is not great, but it's certainly better than average. It's not bad. All right, let's move on and go into a little more detail with standard deviation. So I've given you this chart to help you find the standard deviation for a set of data. This is something we do with small sets of data, really more than anything just to kind of give you a feeling for how we would, or the process we would go through to find standard deviation. But most of the time when we find standard deviation with a lot of data, we tend to use spreadsheets. In fact, I may make a video and show you how to do it using a spreadsheet. But for now, this is how you're going to have to do a couple by hand where you have less data. And so let's look at number 7 here. We need to find the standard deviation for this set of data where we have 4, 8, 9, 11, 13, and 15. So basically, we just need to follow the directions here. It says to find the standard deviation of a set of data. Number 1, we want to find the mean. And so you can certainly do that. And you should get a mean of 10. And so next on number 2, it says make a chart having 3 columns. So I've done that. And my titles for each column would be data, data minus mean, and data minus mean squared. Number 4 tells me, or let's see, number 3 tells me I need to list the data under the column marked data. So let's do that. And then the next step in number 4, it says subtract the mean from each piece of data and place the difference in the data minus mean column. So let's see, for 4, we're going to take 4 and subtract our mean, which is 10, and we get negative 6. So this is what we were just doing a slide or two ago. So here it'll be 8 minus 10, we get negative 2. 9 minus 10, we get negative 1. 11 minus 10, we get 1. 13 minus 10, we get 3. And 15 minus 10, we get 5. Now the next column, we're squaring everything, and basically what that's accomplishing is making everything positive. So when you square negative 6, you get 36. You square negative 2, you get 4. Square negative 1, you get 1. 1 squared is 1. 3 squared is 9. And 5 squared is 25. And let's see what's next. On number 6, it says determine the sum of the values in this data minus mean squared column. So if you add those up, you should get 76. On number 7, it says divide the sum obtained in step 6 by n minus 1, where n is the number of pieces of data. So we're going to take our 76 and we're going to divide by n minus 1. And again, n is the number of pieces of data, so you can see here that would be 6. So we divide by 6 and we get 15.2. And then finally it says determine the square root of the number obtained in step 7. So we'll take the square root of 15.2. Now something to keep in mind here is 15.2, this turned out to be a pretty nice number here. It wasn't even rounded. So usually what I'll do is I'll just take the square root of this fraction here. But in either case, you should get 3.9, so it's about 4. So one of the things you can look at here is these numbers here. So basically what we're saying is on average, the data is about 4 away from the mean, which seems reasonable given the numbers here, if you average these numbers out, or at least as far as how far they are from the mean. All right, so by the way, if you wanted to try this on your own, if you didn't hear, I would encourage you to do this problem here. And I'll give you the answers. And so if you want to practice, you can do this problem here. All right, and that's it for this video.